Building software on cloud AI means accepting a frustrating set of rules. You deal with unpredictable latency that spikes when traffic is heavy, you pay a tax on every single token generated, and if the remote server cuts the cord, your application dies instantly. Then there is the privacy problem. If you want an AI to process your proprietary codebases, analyze your personal chat logs, or sort through private financial data, you have to package all of that up and send it to a corporate data center miles away. The alternative is entirely reversing that data flow. Instead of sending your private life out to the model, you bring the model directly to your data. For that to actually work, though, you need local hardware and software that can process requests fast enough to match the speed of a massive server farm. Without that speed, local development remains a novelty, not a viable engineering path. That brings us to NVIDIA's DGX Spark running a highly specific Llama 3.1 8 billion parameter NIM. This is an opinionated, pre-packaged bundle designed specifically to maximize local inference on this exact hardware. Standing it up takes almost no effort. From a completely cold start to a fully responsive OpenAI-compatible API running locally on port 8000, the entire boot process takes exactly 108 seconds. This chart shows the latency gap between renting and owning. A cloud API usually answers in a few hundred milliseconds, but can easily stall out to 2.5 seconds if you hit a bottleneck. This local Spark setup registers a time-to-first token of exactly 52 milliseconds, pouring out text at a steady 24.8 tokens per second. When an endpoint answers in 52 milliseconds, the user experience shifts entirely. You stop feeling like you're pinging an API halfway across the country and start feeling like you're executing a native function call right on your own desktop. If you're building personal infrastructure and want to see how these localized, on-device stacks actually perform in the field, hit subscribe to follow these hardware audits. Based strictly on these initial speed tests and deployment metrics, setting up a zero-cost local endpoint looks like a viable replacement for an expensive cloud subscription. To verify that speed, we need to run a baseline test. I gave the endpoint a trivially easy prompt. Write a Python one-liner that returns the 10th Fibonacci number, something any developer can eyeball and verify in a second. The response was lightning fast, visually pristine, and completely fictional. The model wrote a script relying on a function called Fibonacci matrix, a dependency it invented out of thin air that doesn't exist in the Python standard library. The standard fix for hallucinated code is to drop the model's temperature parameter to 0. This removes sampling noise and forces the model to choose the most statistically probable response, making the output deterministic. The deterministic fallback was worse. It fed a list of lists directly into Python's built-in POW function, an operation that lacks matrix exponentiation logic and guarantees a system crash on the very first execution. At 24.8 tokens per second, the output feels incredibly snappy. But raw speed and zero latency hold absolutely no value if the AI uses that speed to deliver confidently incorrect logic on a highly verifiable problem. So why does a modern, state-of-the-art model aggressively fail a simple 12-token coding prompt? The answer comes down to quantization. To run efficiently, this specific NIM packages the model using an FP8 profile, meaning its weights are compressed down to an 8-bit floating point format. This creates a strict mechanical trade-off. You aggressively reduce the precision of the model to lower the memory bandwidth it needs per forward pass. You are literally trading absolute accuracy to buy blistering generation speed. That heavy compression allows an 8 billion parameter model to operate comfortably within just 10 gigabytes of the DGX Spark's massive 128 gigabyte unified memory pool. You cannot escape the physics of local hardware. If you choose a small, highly compressed model to maximize your speed, you automatically sacrifice the rigid correctness required to execute exact coding logic. Even with that coding failure, this DGX Spark NIM setup is highly effective foundational infrastructure. You just have to stop treating an 8 billion parameter, 8-bit model as an omniscient coding oracle. It is not an arbiter of absolute truth. Instead, look at what it actually excels at. This is a highly efficient engine perfectly suited for routing logic, summarizing vast amounts of text, and driving conversational pipelines. Because there is zero marginal cost per API call, your software architecture completely changes. You can run thousands of iterative queries without calculating the damage to a monthly cloud billing statement. By mapping the exact boundaries and flaws of this specific quantization, you can safely integrate it into a larger software stack. You build reliable systems by knowing exactly where your tools break. Knowing those boundaries, we can start building. The first use case is a personal retrieval pipeline. You can point this endpoint at a private Obsidian vault or a massive folder of research PDFs, generating complex summaries entirely offline without paying a cent for the generation step. The second application is an unsupervised auto-research agent. You can write a script that forces the model to run hundreds of repetitive code tests, tweak variables, and log results overnight, strictly because you aren't restricted by API rate limits. Third, you can wire this endpoint directly into a local code editor plugin. It serves as an always-on, zero-latency processor for basic text completion that never phones home to a remote server. Right now, this endpoint has a brain, but absolutely no memory. In the next video, we solve that by layering on NeMo Retriever embeddings to vectorize our local data. Taking control of your development means moving past rented cloud interfaces. It means wiring together a fast, completely private nervous system right on your own desk.